Okay, so here is the ramp problem. It's pretty straightforward. The free body diagram's a little tricky. So it says a wooden wheel of mass m consists of a rim with spokes, rolls down a ramp that makes an angle theta with the horizontal as shown above. The ramp exerts a force of static friction. That seems incredibly important. Static friction on the wheel so that the wheel will roll without slipping. If it did not have static friction, it would just slide down, just like the box ramp thing we've been doing. All right. On the diagram below, draw and label the forces, not the components. They hate that, the components, that act on the wheel as it rolls down the ramp, which is indicated with the dashed line. To clearly indicate at which point on the wheel each force is exerted, draw each force as a distinct arrow starting on and pointing away from the point at which the force is exerted. The lengths of the arrows need not indicate the relative magnitudes of forces. So it's not like the Atwood machine where it had like lines and you had to get the length of the arrow right. It's just we got to show where they're coming from this time. That's a little weird. So I'm actually going to use a ruler here. You should probably use y'all's rulers too if you are doing a weird at an angle free body diagram. So I used the ruler to draw a light line that was at 90 degrees to the surface. I would suggest you do the same thing. It's just a really light line. You won't lose points for it unless you put an arrow on it or something. So something useful to do. Anyway, so let's draw the free body diagram. And this is like a cross between a free body diagram to where we are actually looking at the wheel's center of mass. And it's also like a torque diagram, like Miley versus Kim, because we're looking at where forces are exerted. So the first thing is we're going to draw the weight. And weight always comes from the center of mass. And I've gotten this little thing here. I'll do my best to draw a straight line down. Put mg. I'm going to switch colors around just to kind of show you something. Now, normal force would come from the surface. I know normally we do it from the middle, but in this case, because it's also kind of got a torque thing going on, as it rolls without slipping, we're going to go from the surface. And I'm going to do normal force all the way up. It doesn't matter how long your arrows were, again, like they said. But to me, it's important that the normal force comes up through the center of mass. And then last but not least, the friction makes it turn. So it's actually acting on it right here. And it's going this way so that the wheel rolls this way around. But don't put that. I shouldn't have put that. All right. So I will label that force of friction, the blue one. So force of friction. Now you get 2 points for this. You get 1 point for your weight going the right way, and you get 1 point for the other two forces. So a total of 2 points. And they've got to be coming from the right spot. Okay, so this next part is why I picked this question, and I just copied the one out of the returned AP things. See this little, well, I'll read the question. I'll show you what they did. This is a really dirty trick. So, as the wheel rolls down the ramp, which force causes the change in angular velocity of the wheel with respect to its center of mass? Well, one interesting thing is they told you in the question. It says the ramp exerts a force of static friction on the wheel so that the wheel rolls without slipping. Well, when you're changing something's angular momentum, you're basically changing, angular momentum, you need to change its angular speed or angular velocity. Basically, oh, it says the change, it didn't even say momentum, it says the change in angular velocity. What's making the wheel roll? It told you. But here's what they do that's mean. See this tiny little space that like nobody writes in? You need to write the force of friction there. It's got to be in the space where it wasn't graded. Like, you lost the point. So you had to put force of friction here and then explain your reasoning. So watch out for that. One, look out for them giving you the answers because they will do that sometimes. And two, look out for stupid little gaps like that because that's where you have to answer it. So briefly explain your reasoning. And I would put force of friction applies a torque to wheel, making it turn. Or roll or whatever. So that would be, you get your point for that 1 point. But just, yeah, watch where you write stuff and look out for them giving you answers. Okay, so now we have, oh, this is like the derived one. For the ramp angle, the force of friction exerted on the wheel is less than the maximum possible static frictional force. So basically, it's just a little bit of just a part of the friction is making it turn because it's, I guess, moving when it's in contact, or instead of, fully being static. It's kind of like just each point along the wheel is static for a split second. Instead, the magnitude of force of static friction exerted on the wheel is 40% of the magnitude of the force or force component directed in the opposite direction of force, basically, frictional force. That is evil. Derive an expression for the linear acceleration of the wheel's center of mass. That's a good thing. That means we are just looking at the dot in the middle. The linear acceleration of the wheel's center of mass in terms of m, theta, and physical constants is appropriate. I'm going to draw a real free body diagram with components to show you this. Okay, so this is the center of mass. The force of friction isn't acting directly on the center of mass, but the split second that it's making it turn, like if it froze it, like at that instant, it kind of affects it, and that they asked about it in the question. So I just broke this down. Remember, the angle always goes closest to the object, so that's mg cosine theta and mg sine theta. Since this thing is actually accelerating down the ramp, we would want to just look at, I should have done this. This is your acceleration. We're just going to look at the blue ones. So Newton's second law, it's always a good idea to write. And look, we had a free body diagram up at the first one, and now we're doing Newton's second law. That's the way it usually works. They're just trying to trick you into using the one for rotation. So your net force is going to equal your accelerating force, which is just mg sine theta, and then what's slowing it down, force of friction. Now, they said that the magnitude of force of friction is 40% of the magnitude of the force or force component directed opposite the force of friction. Okay, so here's force of friction, it's going that way. What's going opposite? Mg sine theta. So you could just write mass times acceleration equals mg sine theta, weight sine theta, minus, now if you don't know, 40%, percent means of 100 if you're curious, but the way you would write 40%, and I know a lot of you know this, but just on the off chance this is one of those things you missed, like in math when you were younger, 40% equals 0.4. Okay, it's basically 4/10. So this would be 0.4 mg sine theta. And then you want to solve for acceleration, so you would divide by mass. Divide all this by mass. Since they both have mass in them, that can go away. So acceleration should be g sine theta minus 0.4 g sine theta. It's kind of messed up. Okay, so this should be enough if you want to go ahead and get fancy with this. And you notice this is 1 g sine theta minus 0.4. You can say acceleration equals 0.6 g sine theta, but you don't have to. Either one of these is fine. And you get a point. This is 2 points. You get a point for the correct expression of Newton's second law. So that actually that will go up here. Mg sine theta minus force of friction is equal to mass times acceleration. And then you got a point for plugging the point for recognizing that the weird force they were talking about is mg sine theta and putting 0.4 in front of it. So that's 2 points. Okay, this next one's worth 1 point. In a second experiment on the same ramp, a block of ice, also same mass, is released from rest at the instant the wheel is. From the same height, the block slides down the ramp with negligible friction. Which object, if either, reaches the bottom of the ramp with the greatest speed? Okay, well, I think I'll draw a free body diagram for that. Okay, I just copied this, the wheels, free body diagram, and the acceleration equals 0.6 g sine theta from the previous part, you could just draw an arrow or say, look at that other part. I just did this because it makes it easier for the video. So if we look at this free body diagram, the only thing we have accelerating, because acceleration goes this way, is the weight sine theta, because there is no friction of any sort to slow it down. So what I would write here is mass times acceleration equals mg sine theta, and then the masses cancel out. So acceleration is like g sine theta, or 1 g sine theta. So this one's only like 60%. Also, I might state that acceleration is directly proportional to speed. So, therefore, the acceleration of, or therefore, ice is faster. So I would put the block of ice right here. And that is worth 1 point with the explanation. I probably didn't need to write ice is faster down here. I could have just, the rest of this would work. I might have put like a greater than sign. Okay, so now they want the same thing, justification in terms of energy. So it's probably going to be a potential versus kinetic energy kind of thing. So what I would do is, for the wheel, it's going to start off at the top, or it's going to start off at some height. So it's the cube, it's going to have some height right here, and it's going to go down. So it's going to start off with UG. We're going to assume it's at rest. And then as it goes down the ramp like this, it's going to have regular kinetic plus, and it's going to be spinning k rot. So it's got a combination. So therefore, UG, and just for checkboxes, you usually don't have to say it's an isolated system. UG is going to equal K plus K rot. By the way, I'd start off by saying K is directly proportional to speed squared, just regular K. That's important. Okay, then this is the wheel. And for the ice, it's just going to be UG to, it's got a speed, to K prime. Should probably put primes on these. So UG equals K prime. Okay, so I might use a different color here. K, some kinetic energy is lost. Not really lost, but transferred to K rot. Therefore, K wheel prime is less than K ice prime. And this part's important too. So that would justify that, and you would get a point. And that's it.